So we are starting in like 1 minute.
Is it one? I think it's almost 3 minutes, no? 2 minutes at my clock.
Shai, are you okay to start?
I think I'm ready, but I think there is 1 more minute if someone wants to get up in time, but I'm ready when you are ready.
Yes, I think it's at least 1 more minute.
Okay. I think my clock is off.
I think no, it's fine, due to my clock. Przemek?
Yeah. I think we should start. So, hi everyone, welcome to the 6th session of CPM, and the first speaker on this session is Shai Golan. Shai, please go ahead.
Okay. So thank you, Przemek. So today I will talk about streaming k-mismatch problem, the trade-offs between space and total time. This is a joint work with Tomasz Kociumaka, Tzvi Kopolowicz, and Eli Porat. We are all from Bar-Ilan. So we all know the basic definition of Hamming distance, which is for 2 strings of the same length, is the number of mismatches between the 2 strings. And the pattern matching version, we are given text of length n and pattern of length m, and our goal is to compute for every substring of the text of length m the Hamming distance between this substring and the text. In the k-mismatch version of the problem, we are given a threshold k, and our goal now is to compute the Hamming distance except for positions where the Hamming distance is larger than k, which we are just needed to report that this is the case, that the Hamming distance is at least larger than k, but we don't care about the exact value of the Hamming distance in this case. And in the streaming settings of the problem, the pattern is assumed to be given in advance, and the text arrives character by character. And after the arrival of the ith character, our goal is to compute the Hamming distance between the pattern and the Hamming distance, if it's up to k or report it's larger than k, between the pattern and the current suffix of the text of length m. This is also true for the online settings. In the streaming settings, we are also required to use as less space as we can, and for sure, much less than theta of m words of space. So the state-of-the-art result for this problem is by Clifford, Kochumaka, and Porat from Soda 19. They have algorithm with O tilde of square root k time per character and O tilde of k space. Both the time and space are optimal. The time is due to conditional lower bound, conditioned on combinatorial BMM, and the space is optimal due to information theory lower bound, which is stronger. And for the offline settings, the state of the art depends on several parameters. So for small alphabet, the state of the art is the classic algorithm from the 70s of Fischer and Paterson that runs in times sigma n log m, or O tilde of sigma n. And for general alphabet, the state of the art is by Pavel and Przemek, and the running time is O tilde of n plus nk over square root m. And when we compare the two settings, the state-of-the-art algorithm in the streaming settings and in the offline settings, two questions arise. The first question is, can we achieve, although the time per character of streaming algorithm is optimal due to the conditional bound, maybe we can have total running time which match the offline algorithm. Because now the total running time is n times square root k up to polylog. And can we improve it to a total time of minimum between nk over square root m and sigma n? And more general question is, can we achieve something from using more than k space? Can we have a trade-off that if we have more than k space, we achieve something in the perspective of the total time of the algorithm? And we answer the second question by a positive answer. And the first question, we say that if we have online algorithm, which means if we allow to use order of m space, then we can achieve in the online settings the same running time as the offline settings, except up to some log factors. And for the streaming settings, where we want to use less space, the problem is still open, but we still have some improvement if we have more space in the total time. So our main result is stated as follows. If we have some parameter s, and we want algorithm that uses order of s space, O tilde of s space, then we have algorithm with total running time of O tilde of n plus the minimum between three options: nk squared over m, nk over square root s, and sigma n m over s. This is the total running time. And notice that for the online settings where s equals m, the third term here, sigma n, m over s, m and s cancel out, and we have sigma n, which is like Fischer and Paterson algorithm. And here, if s equals m, we have running time, which is just like the state-of-the-art algorithm of Pavel and Przemek that runs in nk over square root m time. And it's important to say that the worst case time per character still matches the algorithm of Clifford et al. That takes O tilde of square root k time per character, which means that we don't pay in the cost per character in order to achieve this improvement in the total time. And the overview of the algorithm is that in the pre-process phase, when we receive the pattern P, we first of all check if it's periodic or aperiodic for some definition of periodicity that is known in the field of this problem, of the k-mismatch problem. So for aperiodic patterns, the problem was almost solved by previous paper of Kopelovich, Porat, and myself from iCalp 2 years ago, and we just, it has the problem that the results was reported with a delay of order k characters, and we removed this delay with a quite standard technique of tail partition. The main part of the algorithm is the algorithm for the periodic case, where the pattern is periodic. And for this case, the algorithm, first of all, find the consensus of the pattern in the text with delay of order s characters. And then, again, using tail partitioning, but in more sophisticated way, based on the black box algorithm of Clifford, Yafromenko, Porat, and Porat from CPM 2008, we remove this delay. And in this talk, I want to focus on the part of finding occurrences of periodic patterns with delay of order as characters. But we will not discuss exactly the details here. We will solve similar problem that will be simple enough, but contains all the main ingredients in our algorithm. So first of all, I want to start from the background, because we somehow based on it and use ideas from the classic algorithm of Fischer and Paterson. So their algorithm based on two mathematical definitions. The first definition is the definition of convolution. So if we have two functions f and g from z to z, the convolution of f and g is a new function that the value of the convolution at position I is defined as summation over all the j's. And for each j, we take fj times g I minus j, which means we go over all the pairs of indices in f and g, that the sum of the indices is I, and we take the multiplication of the actual values of the functions in these positions, and we sum this value into position I. And of course, we want an algorithm that computes the convolution. So one known algorithm is the FFT algorithm, which is an algebraic algorithm that takes n log m time, where n and m are the lengths, or more mathematically accurate, it's the diameter of the functions f and g, as you can see in the figure. And the space requirement, the space usage of the algorithm is theta of m words of space. But of course, there is also the combinatorial way. The combinatorial algorithm is just say, go with the definition, and the definition was summation over multiplications of pair of indices. Just go over all the pairs of indices. And in case that there are many zero entries, and of course, since we consider multiplication of values, we don't care about zero value, then it's enough to go over all the non-zero, all the pairs of non-zero entries in F and in G. And then the total time will be just the number of this pair, which is the multiplication of the size of f and g, if we define the size of a function to be the number of non-zero entries, and the space is just the input size plus the output size, where we have some control on the space usage, in the meaning that if we don't care about all the values of the convolutions, but just the values of the convolution in some specific range, then we can restrict our computation just for this specific interesting range, and we don't need more space than the actual range we want to compute, except for, of course, the input size that we should treat somehow. And the second mathematical definition that used by Fischer and Paterson is the notion of characteristic function. So if we have a string x and some character c, the characteristic function of x due to c is a function that have 1 at every position where x, the character at x at this position is c, and 0 at every other position. As you can see, for example, in this figure, x has 3 different characteristic function by a, b, and c. And the observation that's done by Fischer and Paterson, that if we have text and pattern, this is our problem, and we want to compute the Hamming distance between the text and the pattern at every position, then let's consider for the beginning just one character, just character c. So if we take a look on the characteristic function of the text due to one character, let's say a, t of a, and the characteristic function of the pattern due to the same character a, and we compute the convolution of ta with p reverse a, it's the reverse version of the pattern, then it turns out that the value of the convolution at every position I is the number of matches between the text and the pattern in the character A, where we, when we shift the pattern such that the pattern will end at position I of the text. So for example, here we have 2 matches, and the value, the result of the convolution at this position I will be exactly 2. and the time needed to compute it by FFT is, as we said, n log m, and we need order of m space for making this computation. And therefore, the algorithm of Fischer and Paterson is just repeating this process for all the characters. So we break T to all the characteristic functions related to it, and also we break P to these characteristic functions, and we multiply by pairs the first functions, the functions of T and P by B and by C, and this gives us a computation of the number of matches, the exact number of matches between the text and pattern at every offset. And we just need after that to compute the length of the pattern minus the number of matches in order to have the number of mismatches, which is the Hamming distance, and the total time of the algorithm of Fischer and Paterson is sigma times n log m, because we just repeat the same algorithm from before for every character. Notice that if you consider the algorithm known by Abramson and by Casaraggio, then we just need one simple extra observation. The extra observation is that when we want to compute the convolution of TA and PA, we can use FFT, but we also can use the more combinatorial algorithm, just multiply all the non-zero entries, and we are greedy, so let's take the minimum between them. Let's just compute the convolution of every pair of such functions in time which is the minimum between n log m and the number of non-zero entries in the text and number of non-zero entries in the pattern. Using just this improvement, we can show that this is another way to achieve the result of Abramson and Casaraggio that takes, for general alphabet, instead of n times sigma times log m, we achieve n times square root m log m with just analysis of this idea. And now I want to focus on some toy problem that will be a way to introduce our ideas in the paper. So I want to solve the problem of streaming algorithm for sparse pattern and text, which means let's assume that the pattern and text are from binary alphabet, and they are almost everywhere zero, except of order of k positions where we have ones in the text and order of k positions where we have ones in the pattern. And our goal is just to count the matches of ones. After that, to compute the Hamming distance, it's not a real problem. And we allow to use order of S space as a parameter, just like in the original problem. And we allow to report the results with delay of S characters. So since we allow to report the results with delay of S characters, we just treat the text as coming in batches, which means that after the arrival of every character, we don't do nothing. We wait to the arrival of S characters, and we just do the computation in batches of S characters. And after S characters arrives, we need to report the output not in one index, but in S indices. We need to report S values of the output, S positions of number of matches. And this is true after the arrival of every batch in the text. So if we focus in just one batch, after the arrival of this batch, for example, then we need to report the number of matches between the pattern and the text at every position, at all the offsets that ends in this range. Hence, as you can see, we don't really care about all the text now. Now we just need to focus on the relevant part of the text. So batches that are old history now can be just ignored. And moreover, for the batches that we still interested in, as you can see all these three batches, we can split the computation of the convolution for what convolution we should compute with each one of the batches. So we consider the original batches as blocks of the text. And for example, the first block of the text is not relevant for all the pattern, but just the first S characters of the pattern. And the second, which is more general case, the second batch in the text is relevant for two S characters in the pattern. And in general, every batch in the text that we need to compute its convolution is just related to two S characters in the pattern. Hence, we divide the text into three or in general, M over S, order of M over S blocks of the text. And we divide also the pattern such that each position in the pattern appears in exactly 2 blocks, in 2 blocks of the pattern. And then we compute the convolution of pairs of one function from the text and one function from the pattern, and it takes time, just like we described in the Abramson and Costa-Maggio algorithm, which is the minimum between S, or S log S, called it O tilde of S, and the number of non-zero entries in the block of the text and the block of the pattern. And after a new batch arrives, we just need to remove the first one, shift all the previous batches, and add the new batch. And now for the only mathematical slide in the talk, we can upper bound the time, the total time of computation for the arrival of one text batch by going to sum over all the pairs of functions we have, and for each pair to have the minimum between the number of non-zero entries in the text and number multiplied by the number of non-zero entries in the pattern and S. Everything here is O tilde. And using some pretty simple math, we can upper bound it by K times square root S. Why it's good for? So since for each batch we pay at most K square root S time, we have that since this batch contains S characters and the computation done for this batch is also spread with standard deamortization over S characters, the time per character will be K square root S over S. And since S is at least K, we have O tilde of square root K time. In the perspective of total time, we have the original string is of length n, and we divide it to batches of size S. Therefore, we have n over S batches. Multiply the time per batch with the number of batches, we have nk over square root S total time. Another way to analyze the total time is notice that going over all the algorithm, every non-zero, and we can at any time compute the convolution by the combinatorial algorithm, by multiplying all pairs. If we don't do it, it's just because we have better option. But if we do it, then every non-zero entry in the text will multiply by every non-zero entry in the pattern at most 2 times, because we duplicate every position in the pattern to 2 blocks. And therefore, the total time will be the total number of non-zero entries in the text and the total number times the total number of non-zero entries in the pattern, which is in all K squared. We can do it more mathematically, but this is the reasoning. And another way to analyze is that if we, on the other end, uses just FFT, then we have N over S blocks in the text and M over S blocks in the pattern. And the time for one FFT is O tilde of S. Therefore, the total time will be NM over S. So if we want to summarize, we achieve an algorithm with O tilde of square root K time per character. The space usage for every convolution is just S, so or order of S. So we need just order of S space. And the total time we have is K squared or NK over square root S or NM over S. Take the minimum of all of this. And if we go to the main result, we can see that this is actually very similar to what we get to the main result, to the original problem of k-mismatch. The only differences is that here, instead of K squared, we have N over M times K squared by standard partitioning of the text into blocks of length M. And here we have additional sigma. In our case, sigma was 2. It's binary alphabet, so we don't care about it. But this is the core of the algorithm. In the actual algorithm, we show how to use known technique from previous results that describe how to reduce the problem of k-mismatch with periodic pattern and text into some convolutions of functions with total number of order of k non-zero entries, which is similar to what we did here. And that's it.